Okay, so I'm gonna continue discussing the synthesis of ethers. So the first method of synthesizing ethers is by intermolecular dehydration of alcohols. So first you have your alcohol, and with alcohol, now, like for example, your ethanol, the presence of sulfuric acid at a very high temperature can actually produce your ethane here with the dehydration reaction, and can also produce at around 140 degrees Celsius can also produce actually diethyl ether. So there are two possible products of sulfuric acid as reactants. One is an alkene, the other one is an ether. So for the mechanism, you have your sulfuric acid and your alcohol, and the oxygen from alcohol will be protonated by the proton from the sulfuric acid, forming the OSO3H minus here. So the bond between nitrogen and oxygen here from sulfuric acid go to oxygen here, and now you have your protonated alcohol. So once you have your protonated alcohol, your ethanol, another mole of your ethanol here, alcohol, then attacks your carbon here, your ethanol, bonded to your protonated alcohol, and this becomes your noctiphile, and will use the electrons from oxygen here to form a bond. So you'll have your carbon-carbon and oxygen using the electrons here to form a bond. So what will happen? You'll have your this one carbon-carbon and an oxygen coming from your noctiphile. And once it forms a bond here, the water will leave as H2O. Okay, and you will have your protonated ether here, and you can use another mole of your acid or your water to deprotonate your water here. So we'll use an electron pair for water to extract the proton, and you'll get your ether in the process. So this method is only good for the synthesis of symmetrical ethers. For unsymmetrical ethers, you'll have your another mole, another alcohol in the presence of H2SO4, and again you will have your ROR and another R prime here from another alcohol. You can get another ROR here from the same alcohol, or another ROR, the same second kind of alcohol. So here is only can use a primary alcohol in the process, and actually can get a mixture of ethers. So the exemption is we have a tertiary alcohol here. You'll have a product in the presence of catalyst H2SO4. You'll have your product in this one, and here will attack your carbon here, or this one will attack your carbon here to get your HOH here. Alternatively, you can protonate this one to have your tertiary, your carbocation. Once you have your carbocation, you can have your alcohol attacking your carbocation here to form an oxygen carbon bond. And of course, the process will get your this one here. The first one is the formation of the carbocation to give a good yield ether. Another method is the Williamson synthesis of ethers. In the Williamson synthesis of ethers, we use an alkoxide and proceed the reaction via an SN2 mechanism. So in the SN2 mechanism, you actually have your alkoxide substituting the X here to get your ROR. So again, this one occurs via the SN2 reaction. This R is limited to 1 degree reaction only. 1 degree alkyl halide rather. but R prime can be 1 degree, this one can be 1 degree, 2 degree, or 3 degree. So as an example, you have your sodium hydride and your alcohol here. What happens is that you will abstract, the hydride will abstract the proton from your alcohol. This is a very strong base, and you get your alkoxide side. Okay, O minus can get your alkoxide side, and you have your sodium oxide here, and you'll get the product for your hydrogen. So once you get your alkoxide, then it will attack now your alkyl halide. Like in this case, your bromine, you use this one as your nucleophile to attack your carbon, and this one leaves. So between carbon and bromine here, this one is partially positive, this one is partially negative. So your nucleophile bearing the electrons, and which is also negative, will attack this carbon, which is partially positive. And once it's attacked via the S-enter mechanism, there is a simultaneous bond formation and the bond breaking process, and your product is this one, the same O, and bond with this one, carbon, and CHD, CH2, and then CHD. And so you have your ether process. So another example, you have your sodium hydroxide, and in the presence of water, can abstract your hydroxide to get your proton here and get your alkoxide, sodium alkoxide. And what happens once you have your alkoxide? This here becomes, since this one carbon here contains your alkyl halide, or your halide rather. Once you get your alkoxide, then you can attack this carbon here to form a ring. And what happens? You have your ether, cyclic ether. Another one, you have your sodium hydroxide. Again, the presence of water first. We deprotonate this one to form your alkoxide. Once you get your alkoxide, the same reaction like this one. Once you get your O minus to attack this one by simultaneous by S2 mechanism, and there will be an inversion of configuration. You have here this one to form your oxide. However, in this case, if they are on the same side, no, it's not possible to attack because they're on the same side. The OH and the O, this becomes your nucleophile, cannot attack this one because they are on the same side. So it needs the S2 mechanism needs to be on the back to attack. So this mechanism is not possible to have an epoxide formation, cyclic formation. Another method is the oxymercuration demodulation process. So what we have here, the same way that we prepare alcohol with oxymeration demercuration, it's the same manner that we prepare ether. But instead of water, we use the H2O. So what happens is that we get a mercury. You have your mercury added on one of the carbon. Okay, the carbon that is rich with hydrogen is where the mercury is being added, and the other carbon will have the OR being added. And once you have that one, you can reduce this one. So you have your sodium borohydride, and this one will be reduced to hydrogen. So you'll get your OR here. This one is follows the mechanical virtue selectivity. So the mercury, you get here the carbon bearing the higher number of hydrogen will have your hydrogen being added, CH3, and the other carbon will have your OH, or your, in this case, OR, because we're using methanol instead of water. So another ones, you have your HGO. So this one, we're using HGO2CCF3, and the other one is sodium borohydride. So you have the isopropyl alcohol, and this a similar number of hydrogens. You get either either carbon, you get the same product here. So you have your O carbon, O CC, the isopropyl alcohol here. And here is where the other one is where your sodium, the other one is where your HGOCCF3 and a reduced then it will be further reduced with sodium borohydride with hydrogen. That one. So the other reaction is the third butyl ethers by alkylation of alcohol. So how does it happen? So you have your alkene and you have your sulfuric acid here. What happens is that you have your third butyl group protecting group here. So in this reaction here, you will add your, you have your addition, you have your proton added to your hydrogen here. Okay, so this carbon here, you will have your hydrogen added, and the other one is where your OR being added. So you'll have your O carbon, the O carbon here, and this is where the hydrogen is being added. Remember your H2SO4 in water where your hydrogen is being added to the carbon bearing greater number of hydrogen. A third butyl ether can be used to protect the hydroxyl group of 1 degree alcohol while another reaction is carried out in some other part of the molecule. A third butyl protecting group can be removed easily by treating the ether with a dilute solution. The example here, synthesis of this one from this, and you'll get your PRMG.